Swayam Prabha. Digital India. Educated India.
Okay, so now when we come to exit, now we do a division, right. Now I say div ECX, right, div ECX, because B is stored in B is mapped on to ECX, div ECX. Now what have we done? So we are only giving whatever the denominator here. Where is the numerator? Where is EAX? So you have to do EAX by ECX, right. EAX is storing A, ECX is storing B. I should do EAX by ECX, right. But here I need not, I do not do div EAX by ECX, because div is a complex instruction. Always the numerator will be in the EAX register, right. Div is a complex instruction, so I do not explicitly give two different operators. For division, whenever I want to do division, right, the numerator should be in the EAX register. I will only specify the denominator. Able to see that? Fine. Why? You should ask Intel, okay, but this is how it is designed. There are many reasons for why it should be done. Okay. So this addressing mode, 1 minute, this addressing mode where I am not telling explicitly where the numerator is. If I want to do division, there are two operands that are necessary. One is the numerator, another is the denominator, but the numerator I do not explicitly state that this is the numerator. So this addressing mode is called implicit addressing mode, right, implicit addressing mode. So we have already seen three addressing modes. What are that? Immediate addressing mode, where the value of the operand is available with the instruction like move EAX 0x0, that 0x0 is the immediate operand. Then we have seen a register addressing mode, where we use a register as a destination or source. Then now we are seeing what is called an implicit addressing mode, where the thing is hidden, we do not write it, it is implicit. EAX being a numerator is implicit. Now I do div EAX by ECX. Now the result of this, where will the result of this get stored? See, if you say move EAX 0x0, the result is basically EAX getting initialized to 0. Move ECX 0x5, the result is ECX gets initialized to 5. Increment EAX, the result is stored back in EAX itself, where the source and destination operand are same. But if I say div ECX, where will it be stored? The answer will be stored in two registers, namely EAX and EDX. EAX will store the the quotient, the quotient, and EDX will store the remainder, right. So when we do integer division, the quotient comes out and I can also have a remainder. So EAX will store the quotient and EDX can store the remainder, right. So now what I am saying, that once I do div ECX, your numerator is lost, the original numerator is lost, the original numerator should be 10, right, that is lost, correct. Now instead I will store the quotient and the, so you get EDX in this case. When I do 10 by 5, your EX will be 2 and EDX will become 0. Now you move the content of EAX into some memory location, which I give by 0x B1000. You move the content of EDX into another memory location, which I give it as 0x B1004, okay. So 0x B1000 is an address in the memory, 0x B004 is an address in the memory, right. So I go and store the value of EAX in B1000 and the value of the remainder in B1004, correct. So what is this called, this addressing mode? This is called memory addressing. So now we have seen 4 addressing modes: immediate, register, implicit, and now memory addressing. Correct? Are you able to follow? Yes or no? Why are you whispering yes man? Say yes. So this addressing again, memory addressing, this is a memory direct addressing, because I give the address directly there. To which memory location should I write to? I say 0xb1000, I give the address directly, and I put those 2 square brackets, which is very important, which says that I am writing into that memory, right. So this is called memory direct addressing. Okay, right, you asked some doubt. Yeah.
So what if we have to do C is equal to B by A?
C equal to B by A. Okay, it's very simple, right? Move, B should be in EX and same, right? Yes.
After this instruction is executed, the value of A is being changed.
Yeah.
So if you have to use that value of A
Again, that's a problem. You have to be careful. So that's why I said no. General purpose registers are scratch pads. So once you scratch on it, you throw it off. Suddenly you want now, you won't get it. Okay. So you should be careful while compilation. What if? After C equal to A by B, C equal to B by A. Yeah. So that's why we have no EAX, ECX, EDX, EBX and all we have, right? So in another register you use EBX, EDX and all are there, no? Yeah, then you put it in memory and get it back again. Oh, that's called register spilling. I'll talk about it. Good. Now let me ask you a very interesting question. Why B1000 then B1004? Why B1000 and then B1004? They are addresses. Size of, so we are talking of integer. So in every memory allocation I can store only 1 byte. So this is called, so x86 has what we call as a byte addressable memory. Okay, byte addressable memory. That means for every byte I have an address. So if I have a byte addressable memory, then integer is 4 bytes in normal compilers today. So at least the compiler I am using here is at 4 byte integer. So B1000, B1001, B1002, B1003 will store the quotient. B1004, B1005, B1006, B1007 will store the denominator, sorry, remainder. Yeah.
So will the second instruction actually be executed when we run the C code?
Which second instruction?
When we do C equals A by B, it seems unnecessary to store the remainder as well, right? We anyways lose the remainder.
Yeah, but in this case, yeah, will it? Yeah, it will store, right? You can, if you want, you can. In this case, you don't need it, but if you can, if you want, you can. So let me say some okay, some M, yeah, some. It depends. No, what I am saying is that EDX will have the remainder.
But there's some actual protocol which is followed, right? Like when conversions happen.
Yeah, this last instruction may not be dumped by the compiler. So this is just an attention seeking for you to tell you that remainder also is generated, and importantly your EDX gets screwed. Okay, it gets changed, right? If you use EDX for some value and you go and execute DVECX, these two registers get completely changed. That's the most important point that we are trying to do. So it is not that the source operand is implicit, even the destination operands can also be implicit, right? The source was EAX, that was implicit. The destination is EDX, that is also implicit here. But interestingly, the denominator is not changing. Okay, right? Why? No, I could have made the denominator store the remainder, no? Why poor some other totally uninvolved register, why I am going?
If it becomes 0 at the end,
Huh?
you use it again for division later, it becomes 0.
What is so sacrosanct about?
It needn't be the same register all the time. It
Huh?
needn't be ECX all the time, it can be anything, right? So,
Right. If I say div EDX, EDX will change anyway. Right? That's the question. So it need not be ECX always, but the two operands where I will store that has to be told in advance. Hey, when I execute div, EAX and EDX will change, right? And if you use EDX as your denominator, anyway it goes for your toss, okay, right? Do you understand this? So this is so slowly this is a complex instruction set computer. That complexity slowly we will try and understand this, okay.
So when an actual C program is converted,
This is an actual C program. Yes.
so are these values stored in the memory or are they directly stored in the register?
It all depends. If you say A equal to 0, B equal to 5 and all, right, then it will compile like this.
But what if I want to reuse it?
Then you mapped on to A. If you want to, here also I am reusing A, right? I am reusing A several times in that. After that you want to, then you have to, if you can, if you want to use reuse A after division, then at this point you have to move A to some memory location or some other register, okay, right?
so,
Yeah.
so can we feed in 0x B1000 for instead of ECX here? Some constant for division, what's the parameter?
Division, yeah, you can put div 0x within bracket 0x B1000. Yeah, we can you can give a denominator as a memory operand. We can, I don't know. So that's what you can go to the Intel manual.
Talking about constants.
Huh? Can I give a constant as denominator? So all these things you can see. Okay, now this question has come up. Like, let us go. I'll just finish this slide and introduce you to the manual, specifically with the div instruction. Manual is here. These are all the jump instructions. Okay. The conditional jump instructions, right? JO, jump on overflow, jump if there is no overflow, jump if the sign bit is 1, jump if the sign bit is not 0, jump when equal, jump if 0, both means the same. JE and JZ are same. Jump when not equal to is equal to jump when not 0. Jump if below, jump if not above or equal, jump if carry, jump if not below, jump if above or equal, jump if not carry, jump if below or equal, jump if not above, jump if above, jump if not below or equal, jump if less, jump if not greater or equal. All these things are very quite easy. JLE, jump if less than or equal to, JNG, jump if not greater, both mean same. So all these acronyms you can use, right? These are assembly language instruction, and this should be followed by an arithmetic instruction. This should follow an arithmetic instruction, and this will touch those flags. So what are all those flags? OF is the overflow flag, SF is the sign flag, ZF is the 0 flag, CF is the carry flag, and PF is a parity flag. You know what is parity? Odd even parity. If in a byte if you have even number of ones, then it's even parity. Odd number of ones, it's an odd parity. Okay. So this will check parity flag is for even parity. That means it will be set to 1 if the result is even parity. Otherwise odd parity. And then we have some conditional registers, CX. If the CX is 0, ECX is 0. So all these different types of conditional jump instructions are there, and this you can use these combinations to model any loop, any type of condition within a loop, right? So that's very important. Now this is another snippet where A is 1 and ECX 5. but I go and do a do while rather than a while loop. That means surely it will be executed once. So I just do increment Ex, then I compare, then if it is non-zero I go up, if it is 0 I just come down and do again div ECX and so on. So this is how a do while loop can be translated, and you see there is a one-to-one translation here. Whenever I encounter a loop, put a label there, right, and then check the condition there itself. If it is a while loop like what we saw earlier, if it is a while loop we immediately check that condition and do the necessary jumping. If it is a do while, then put the body of the loop here, then go and check the condition and do the necessary jumping. So that is it. Now we will just go into the manual. Now, yeah, about this manual you can read in your summer vacation, okay. Instruction format will take quite long time for you to understand the instruction format. That is not necessary. Let us go to chapter 3, instruction set reference, okay. Okay, so our whole thing starts with AAA instruction, ASCII adjust after addition, that is 318. So we can go to 318, yeah. So let us take the add instructions, okay. Add. So these are all the varieties of add you can have. You can just say add AL with an immediate 8. AL, you know, I explained what is AL, right. Add AL with immediate 8. Immediate 8 is an 8-bit operand, 8-bit value, right, immediate operand. Add AX with immediate 16. Add EAX with immediate 32. Okay. Add RAX, RAX is for the 64-bit extension, but there also we can immediate 32 you can add. Add R/M8 with immediate 8. R/M8 means the left hand side operand can be a register of 8 bits or a memory location of 8 bits. R/M8 with immediate 8. Or add R/M8 with immediate 8.
Destination of the add operation.
Destination will be first is destination, second is source, always.
When we have like add A comma B, it stores in.
Yeah, the add AL comma immediate 8, obviously AL should be the destination, right. Immediate 8 is a constant. So from that you can infer. So always first is the destination, second is the source, okay. So what do you mean by add R/M8? Add immediate 8, add the immediate 8 to the content of a register, 8-bit register, or a content of an 8-bit memory, meaning 1 byte, right. Similarly R/M16 with immediate 8, R/M32, all varieties of add which human being can ever conceive of, all these are there. Okay, I can have add R64 comma R/M64, this is for the 64-bit operations also, okay. Then at the end please note that, so this is the operation will be destination is destination plus source. So one will be destination will be destination plus source. And please note that this instruction, importantly please note here, it will affect these flags. What are the flags it is going to affect? The overflow flag, sign flag, zero flag, auxiliary flag, CF is some what? Carry flag, and PF is parity flag. All these flags it will affect. Then it can also give you an exception. For example, it can give you memory divide. This is add, right? So if your memory operand is outside your segment, it can give you, if the destination is located in a non-writable segment, if a memory operand effective address is outside segment limit, if the okay, so this is, as I told you yesterday, we are talking about protection, right? So we will talk about this in great detail, but it can give you a set of exceptions if you are trying to access memory which you are not allowed to access, right, both for reading and writing. Okay. So are you able to get an understanding of this? Now let me go into something and tell you this. So let me say I want to move, sorry, let us say add EAX comma 0x1000. What it will do? What will this instruction do? Okay, it will take the 32 bits starting at 1000, 1001, 1002, 1003 stored at these 4 locations. It will take that 32 bits, add it with the content of EX and store it back in the EX. So now if I say add AX comma 0x1000, it will take the 16 bits that are stored in 1000, 1001 and add it with AX and store the result in AX. If I say add AL comma 0x1000, then it will take the 8 bits that are stored in 0x1000 alone, add it with AL and store the result back. Now let us take these 3 instructions, add EAX, add AX and add AL. See, the opcode, see this line basically talks of the opcode, which tells you what the operation is. Both for R16 and R32 the opcode is the same. Okay, right? But what it will do is, there is a prefix that will be added, right? There will be a prefix that will be added in front of the 01, which will say that this is a 16-bit instruction. So please note that the opcode is same. To distinguish between whether it is an R16, M16 comma R16 or M32 comma R32, we can't do it here because the opcode is the same. So before the opcode there will be a prefix that will be added which will say that this is a 32-bit instruction or 16-bit instruction, right. So for every opcode there will be a prefix which will distinguish whether it is a 16-bit instruction or 32-bit instruction. In some sense Intel was too lazy, it has finished the 16-bit encoding. Now to convert to 32-bit it did not want to do another fresh encoding. So what it does is, in a 16-bit instruction, if I put a 32-bit prefix in front of that 16-bit instruction, it will start behaving like a 32-bit instruction. You are able to get this, right. So this is how Intel moved from a 16-bit architecture to a 32-bit architecture. So you can have a 16-bit instruction. Now if I want to make it a 32-bit, put one prefix in front of 16-bit, then it becomes a 32-bit instruction, okay, right. So this is how you start reading this manual. It does not look scary. So first 2 or 3 instructions you will struggle, after that you will get used to it, okay. So okay, so with this I stop my introduction, okay. Any doubts? Don't tell me you didn't have doubts, you will have doubts. Yeah. Where are the opcodes? It's in the manual. Are they used somewhere? When you compile it, you get opcodes, right? The opcodes are the one which the machine can understand, correct? So when you compile the C code, for example, okay, good question. So this is the C code, this is a human readable form. If I write 0110, you can't read it, right? What you see on the right hand side, sorry, what you see on the right hand side where my hand is rotating, right? This is a human readable form of your opcode. all your move, add and all will be, there is an equivalent zeros and ones, right. But I can't write zeros and ones here because then you can't understand that. So this is called a mnemonic, which is a readable form of your opcode. But what you see on the right hand side is basically zeros and ones. It will be represented zeros and ones. These are the things that will go into your system, and your machine, your architecture will understand only those zeros and ones. It cannot understand the C program that you see on the left hand side. It will understand the assembly program that you see on the right hand side. Okay. So this move, compare, etc. are human readable versions of your opcode. Ultimately this will be in binary, and this is what your system will understand. System cannot understand do while loop and all, but it can understand this. So this is what will go into your computer, into your architecture, and the architecture will execute, right. Are you able to follow? Yes or no? Yes. Okay. Fair enough. Okay.